Now, with the normal model and how we use it, the model shows us so much information in terms of what's expected, what's likely, what's unlikely. It can give us a good sense of possible outcomes to see for that type of data. But what if we wanted to compare it to other data that had its own expected value and its own spread of those values and its own probabilities? If we want to compare unlike events, it can be difficult to do without making any changes. So that's where we're going to change to the standard normal model, which is going to rely on these things called z-scores. So you're going to see z come up, and we'll call them z-scores for our calculations. But it's going to be these values such that they're standardized, meaning we want to use the mean and standard deviation. That's very important. But we kind of want to remove units from it, and instead of comparing them numerically, we're going to use the standard deviation as a ruler so that we can get a sense of the event that we're looking at, how far was it from what was expected, and how many standard deviations away was it. So with that, what we're going to do is end up creating a number line of sorts. We're going to have this number line that goes on forever, and at the center of that number line is going to be 0. And with the z-scores, if we think of this as the number line for our z-scores, if we're thinking in terms of how many standard deviations away from the mean are we, and we get a value of 0 out, that's going to be landing at exactly the mean. So if we get a z-score of 0, that means that value is exactly equal to our average that we would expect. Then we're going to use this number line of 1 and 2 and -1, -2 around it. And when we land on this positive side, like getting a z-score of 1 or 2, it's telling us how many standard deviations away from the mean. So being at 1 would represent 1 standard deviation above average. 2 would represent 2 standard deviations above average. So positive z-scores are going to represent results that are above average. And the negative values, like getting -1 out, is going to represent being below average. So having a negative z-score. And -2 would be 2 standard deviations below average. So this will be below average. So there's a little glimpse at z-scores, but let's see how this actually applies. So we're going to go back to that Portland rainfall example. So we're going to have Portland rainfall, mean of 40 inches, standard deviation of 8 inches. So in fact, let me just kind of put that together here. Portland, and it'll be Portland rainfall that we're looking at. We expect rainfall of 40 inches, and on average that'll deviate by about 8 inches. What we're going to do is compare that to wind speed in Chicago. So wind speed in Chicago on average 10 miles per hour, standard deviation of 2. So Chicago wind speed, we expect it to be 10 miles per hour with a standard deviation of 2 miles per hour. So these two things operate very differently. They have different units, they're measured differently. One's a rate, one's measured with a ruler. It operates very differently. So we can't just compare them directly. So what we're looking at is Portland had rainfall of 24 inches. So we're seeing this one result of 24 inches, and Chicago had a wind speed of 13 miles per hour. And what we want to see is which one was more extraordinary. Or we could think of is this phrasing here of which was more extraordinary. You could think of which was further from expected. Further from expected, so further from the mean. So looking at 24, which is representing 24 inches of rainfall, and comparing that to 13 mile per hour winds, we can't just say like 24 is larger than 13 and be done with it because they operate very differently. What we'd want to do is see like Portland rainfall, we're getting a number that's way below average there. With Chicago wind speed, we're getting something above average. But in terms of distance from the mean, it's kind of hard to see here. Well, we could see like this is 3 miles per hour above average, and what this is 16 inches of rainfall below. But just having that distance is enough because of the spread of the data. Because if our values are expected to be really close, then if our event is just slightly far away, it's considered extreme. Whereas if our standard deviation is really large, which would mean we expect our data to be very spread out, we could have a number that looks far away, but in terms of it being extreme, it actually isn't that extreme because we expect things to be far away. So our z-score formula takes all of these pieces into account. This numerator, what we're going to do is this will find the distance between the event and the mean. So that'll give us an idea of how far away we are, but then we need to account for the spread. So that's where we're going to divide by standard deviation. So let's see how this works. So that z-score for that 24 inches of rainfall. So for the numerator, we want to see how far is 24 away from the mean, and make sure the order is correct here. It should always go x minus the mean. And then once we get an idea of that distance, we want to figure out how many standard deviations that represents. So we're going to divide by 8. And for Chicago wind speed, same idea of the event of 13 miles per hour minus the mean, and then divide by standard deviation of 2. So with Portland, we're getting a z-score of -2 out. And how I could translate that into words is, again, this is giving a distance in terms of how many standard deviations away from the mean. So I could say like 24 inches of rainfall in Portland is 2 standard deviations. And because it's negative, this would be below average. So with this wording, we get an idea of which side we're landing on, positive or negative, so it's below average. And then we get an idea of distance in terms of standard deviations. This went 2 standard deviations below average. Whereas with Chicago wind speed, if we calculate that one, we're going to get a positive 1.5. So with that, we could say 13 mile per hour wind speed in Chicago is 1.5 standard deviations above average. So now we get an idea of distance in terms of standard deviations. In this case, we're landing above average. But what's important here is now we have the same units. That 24 inches of rainfall, now we have something to represent that doesn't work in terms of inches. And with Chicago wind speed of 13 miles per hour, now we have something in terms of units of standard deviations and not miles per hour. So we have these two numbers that we can compare, and we can put them on the same number line. So what we've done is we've standardized our data, where Portland had, in fact, let me write it, Portland had this whole setup for rainfall that was normally distributed with a mean of 40 and standard deviation of 8, and Chicago had its own setup for a bell-shaped curve, normally distributed with a mean of 13 and standard deviation of 2. But what we did is by changing into z-scores, now we can map them on the same number line. So what we did is instead of using that 40s and 8s or the 13s and 2s, now we have our bell-shaped curve built around z-scores. Just like the number line that I started with at the beginning of this video, is we have this idea of we expect to land at the mean, which 0 as a z-score is landing exactly at the mean. And then if we land here, which, like, if this was Portland rainfall, we'd have 40, 48, so on and so forth, where +1 represents one standard deviation above the mean. Numerically, 48 would come through, but 1 as a z-score standardizes it. And where in terms of Portland rainfall, we'd have 32, as a z-score, we can use -1 to represent that one standard deviation below the mean. So now what we could do is map where does Portland and Chicago land on this number line. So Portland with a z-score of -2 is out here, and Chicago wind speed with a +1.5 was landing here. So if we want to answer that question of which event was more extraordinary, well, what we'd want to see is which is further from 0, because 0 is the mean in terms of z-scores. So Chicago was 1.5 away, but Portland was 2 away. So this event in Portland was further from the mean. So with that, Portland had the more extraordinary event. So with that, we get an answer to our question. We need to look at z-scores to actually compare those values. So this right here, with that number line of 0 and standard deviation of 1, that's our standard normal distribution. You can see a definition of the distribution here. Notice the difference between what I wrote there for the standard normal distribution versus what I wrote up here. So it's still, what stays the same. In fact, what I'm going to do is just kind of cover up that piece that's different. All of these are being defined by normal distribution, mean, standard deviation. Just when we work with z-scores, it's always implied of having mean of 0, standard deviation of 1. That's what comes through when we calculate these z-scores and standardizing those values. Now, with Portland and Chicago, my variable was x. When it was with Portland, x represented amount of rainfall. With Chicago, it represented amount of wind speed. With the standard normal curve, our variable, and this number line that we're writing on here, is always in terms of z-scores. So instead of using x there, we use z to represent our z-scores. So something to be careful of is wording. If they're talking about a standard normal curve, you're using these z-scores. If they just say normal, meaning they're leaving out that word standard, then you're working with x. So just be careful. All right, so standardizing into z-scores, the shape doesn't change, meaning if our original populations were bell-shaped, when we make z-scores, it's still bell-shaped. Center becomes 0, so we have a mean of 0. Spread, in terms of standard deviations away, becomes 1. So every time we work with z-scores, mean of 0, standard deviation of 1, every time. So normal distribution model is a normal model defined by any mean and any standard deviation. Standard normal model, mean of 0, standard deviation of 1. And we can calculate z-scores with our formula right there. Let's look at a few examples. So with these two right here, let's say I wanted to find some probabilities. This first one is saying, what's the probability that z is less than or equal to 1.5? Now the notation here is very simple, and it might look like you don't have enough information here, but a lot is implied by this notation. So what's implied is, because that's saying z right there, we're using a normal model with a mean of 0, standard deviation of 1. So what I could do, I could even start a picture here of a bell-shaped curve, my number line, and we're looking for the probability that z is less than or equal to 1.5. So 1.5 is my cutoff, and I want to find the probability of being less than or equal to that value. So I want this area to the left. And that's where I go to GeoGebra. So in GeoGebra, just to show you kind of from the start here, you're at your GeoGebra website, more apps, go to probability, and when you need to use the standard normal model, it's always the first model that's going to be loaded here. So where our first step would be to change the mean and standard deviation, because we're working with z-scores, you want that mean of 0, standard deviation of 1. So that's all set up for us. So we want the probability being less than or equal to 1.5. So we're doing a left-sided calculation, and we want our cutoff to be 1.5, which will be a 0.9332. So with that, 0.9332, or if we needed to write a sentence, 93.32% chance. Let's look at another one. So we have this probability that z, which again, because it's using z right there, that sets our mean of 0, standard deviation of 1. So we get that information just from using that letter there. And then if I draw a quick little picture here, then what we're going to do is go to negative 0.3, which is maybe about there, and positive 0.5, which is maybe about there, and I want to find the probability being between those two values. So if we go to GeoGebra, we're going to look between, so this will be our interval, and then we'll have a negative 0.3 and a positive 0.5, which will be a 0.3094. Or if we needed a sentence, 30.94% chance. So when you're given probability notation like this, if they're using X here, they'd have to tell you about the mean and standard deviation that they want you to use. But if they just write Z there, it's implying mean of 0, standard deviation of 1. It's all included together. All right, one more example here, kind of like comparing our Chicago wind speed and Portland rainfall. We're going to compare the results of two exams that have very different expected averages and has different spread to the values. So we have an incoming freshman, and they took a French exam and a math exam. So they list her scores. In terms of determining what value they're giving represents X, it can actually often be easier to just go and find the mean and standard deviation, and X will be the other value. It's coming from the event that you're actually seeing. So like we're comparing this freshman's results to everyone else. So like she had a score of 82 on the French test. So that would be her X value. And she had a math score of 86. So that would be the X values because those are specific to her, a specific event that we want to compare to. So for the French exam, there's this overall average of 72 points with a standard deviation of 8. And we want to compare that with the math score of 68. Standard deviation of 12. And we want to see which did she do better on. So something to think about that I didn't necessarily call out clearly when we looked at Chicago wind speed and Portland rainfall, negative and positive didn't matter here. It didn't matter below average versus above average because the wording just said extraordinary, which just means different, which was more different than what was expected. So that's where we could just look at overall distance. With this exam score question, where we want to see which one did she do better on, to see better, it should really be above average. Or it should be the higher of the scores. So sometimes it'll imply wording like that of only looking at the negative values or only looking at the positive values based on how they come out. So let's find our two z-scores. In terms of comparing right now, so like we could see she got a higher grade on the math score compared to French. Something to think about is she scored way above average on the math test, more so than the French test. Like, she was above average on both of them, so she did well on both. But the math score was more impressive in terms of above average. However, notice that there's more variability to the math scores than the French scores. That's going to mean that the scores we could see for the math exam are more spread out. So what that does is it kind of changes the game where, yes, we're absolutely above average, but it might not come through as that far above average just because we expect kind of a longer number line. We expect to go further out there. So that's where kind of a wrench comes in, that we can't just intuitively answer here. We need to take into account spread. So that's where we're going to grab our z-scores. So z-scores for the French exam are x value minus the mean divided by 8, and that's going to be a 1.25. For the math exam, z-score of 86 minus 68 over 12, which will be a 1.5. And basically we want to see which one's further above average. If it helps to draw the number line that we're working with these, I'm quite visual, so I like to draw the pictures to go along with these. French exam's at 1.25, so maybe about there, and the math exam is at 1.5. And what we'll notice is that we want above average with which both of them are, but that math exam is further above average. Again, as we get out to 2, anything at 2 or above is considered unusual, like that would be unusually above average. So we're getting close there with that math exam of getting into this territory of where she scored way higher than everyone else. So with this, because her math score was further above average, the math score was better. So those are z-scores. We'll primarily use them to compare unlike events, just like we did with the French and mathematics here. If you look at other resources for statistics, like other textbooks, actually even our textbook, and videos, if you look at videos with Khan Academy, a lot of statistics resources heavily rely on z-scores. Like every question they do, they switch to z-scores first. And that was really necessary when we use these z-score tables. If you look up z-score tables, you can see is these tables of z-scores that line up with every area associated, and that's how we used to look at these probabilities. And even a lot of resources, like this is why GeoGebra starts out in the standard normal model, they'll change every question into this form to find the answers. So even the solutions I found in the past 2 videos could have been done with z-scores, and a lot of resources would show it that way. And basically they do it so that you don't edit mean and standard deviation. However, my feeling is it's nice to apply it to the actual scenario. Like this 0s and 1s can be hard to see how that relates to our actual data. Like seeing Portland rainfall in this picture here is tough. Whereas we have the tools to edit mean and standard deviation, and now we can really see how that Portland rainfall comes through. So there's kind of 2 ways of teaching this, and I've gone through what I find is most applicable and even simpler, but I just wanted to give that little speech on it just in case you're looking at problems in a textbook or other resources. You're like, why do they keep using z-scores? It is a method of going through this. If you prefer that method, you would get the same exact answers out in all of the examples we've done so far. But how I'm going to ask questions of you in terms of z-scores is more like this scenario here. And in our participation worksheet, you'll see some scenarios of finding probabilities like we did in these first 2 examples. But really, I'm going to rely on this comparing of 2 different scenarios.